Thanks for coming out tonight. I'd like to tell you tonight about a conversation. It was a good conversation. It was a conversation which changed my life. One in which Stephen Hawking and I basically tried to get a grip on the multiverse. And it all started in '98. I had gone to Cambridge from Belgium, and Stephen took me on as his grad student to work on cosmology. And gradually we found ourselves on the same scientific wavelength. We grew close. We continued to talk, continued to collaborate, and we finished our last paper basically shortly before his death in March. 20 years later. So you might say, well, 20 years is a long conversation. And that's true. But I think slowly. Stephen spoke slowly because he lost his voice. And so the whole thing had to happen through a computer interface. And moreover, the subject was confusing. We were talking about the multiverse. We were trying to get a grip on it. And our journey, as you will see, basically led us to the most extreme realms of our universe, where the laws of science are just really strange and screwy. But still, I'd like to convey to you tonight the essence of this conversation. All right, I didn't come all the way to Christiana to just talk about how it was like with Hawking, right? And you may not like it. I mean, it's strange, the sort of picture, the worldview, so to speak, because this comes down to a kind of worldview, the worldview that emerges. But we can't help it, right? We looked at it, at the universe, we thought about it as best as we could, and the kind of thing which is emerging is just really strange. If you really don't like it, you'd have to go somewhere else, like to some other universe, where the laws of science are philosophically more pleasing, but this is the way it seems to work out, and ultimately that's our world. So what are these extreme realms of the universe that I mentioned? Many of you will know Hawking from his famous book, A Brief History of Time. From the Big Bang to black holes. These extreme realms I'm talking about are black holes and the Big Bang. Black holes are collapsed stars. The Big Bang is the beginning, right? These are extreme realms because time, as we know it, ends inside black holes and it begins at the Big Bang. And those are the realms of our universe where our very basic notion of reality is tested, is challenged as much as we can. And those were the realms we were led to. Now, what's the foundation of this whole story, of this whole conversation? The foundation, clearly, is Einstein's theory of relativity, Einstein's description of how gravity works. And according to Einstein, there's a connection between matter on the one hand and the fabric of space on the other hand. The mass of the Earth here bends the fabric of space in its environment, and it makes the moon automatically orbit the Earth and the Earth orbit the sun. So gravity, as we experience it, according to Einstein, is really a manifestation of the bending and the warping of space and of time. It's a very strange notion, very different from what we're used to, but it turns out that's the way it works. And Einstein's theory has been very well tested. Now, nothing can escape this bending. Even light rays, when they move through space, images will get deformed when they pass through a region of space which is warped and bent. And astronomers see this. This is a picture, a real picture, of a galaxy which is accidentally lined up behind another galaxy, behind this one, and the image of the galaxy which is behind that one is deformed because the middle one is bending space in its vicinity. And so that creates all these nice rings and arcs on the sky which astronomers sometimes see. Of course, Hollywood shamelessly exploited Einstein to get a picture of a black hole here by putting a star behind the black hole and imaging how light from that distant star gets deformed when it passes the extreme warped space in the environment of the black hole. But now, what is a black hole? A black hole emerges when stars run out of fuel. When big stars run out of fuel, gravity makes these stars collapse. There's nothing we know that really can stop that collapse. And because, as I mentioned, Einstein's theory relates mass to deformations of space, when a mass gets compressed to really dense object, the warping of the space, the valley in its environment, gets more and more deformed. You create a deeper and a deeper valley. That's sort of what pictorially given here. But the problem is, it goes wrong all the way in the center of the black hole. The fabric of space and time is basically torn apart. So Einstein didn't like this. If these results were real, he said, it would be a true disaster, especially for him, because his theory broke down. Einstein's theory brings space and time from a kind of metaphysical thing which we think just exists into a physical thing which can change and warp and bend. But Einstein's theory does say can't deal with space disintegrating and the fabric of space just like being torn apart. But that is precisely what's happening inside black holes. Time really comes to an end inside black holes. Black holes are black because these deep valleys, they capture the light, unlike that sort of arc which you saw earlier. If you really have a black hole, then there's a region surrounding it from which light cannot escape. Now you might say, well, two things. Well, fine, okay, that's all good, but does this really happen? Well, it seems it really happens. And in fact, one of your previous speakers, Kip Thorne, probably claimed that he saw black holes through their gravitational waves which are emitted or generated when two black holes collide. So you can't really see black holes directly, but out there in the universe, there are lots of pairs of black holes, and sometimes they get locked into some orbit. When they get locked into an orbit, because there's a connection in Einstein's theory between the mass and the space geometry, you create ripples of space, really ripples in the fabric of space, which propagate outwards. If you find yourself in the wake of such waves, then you're going to shake, you're going to be stretched and bent, as shown here. And that is precisely what Kip and his colleagues and the LIGO collaboration claimed to have measured using very, very sophisticated large detectors, one in Livingston and another one in Hanford. Since then, there are very few scientists which doubt the existence of black holes. That is because the pattern of the gravitational waves which they measured, it's exactly like Einstein's theory predicted. So you have there in the universe objects which are as big as Copenhagen, and they weigh 30, 40 times the mass of the sun. So you have huge, huge objects which basically can't be anything else than black holes. And so that Einsteinian situation, that Einsteinian description of gravity, is the sort of context in which our conversation took place and in which Stephen Hawking first arrived on the scene. His PhD advisor in the 60s set Stephen to work on the problem of time. Evidently, the insight of black holes was a good test case. And so Stephen started out thinking about that question. And it was already mentioned in the introduction, he had sort of a kind of a motto to go through life. Here it is. My goal is simple. It's a complete understanding of the universe. Well, there we go. What he meant there, of course, was not whether he could predict the outcome of some sort of event tomorrow or some random event, but whether the laws of science are complete, whether the natural sciences can really describe in some sort of mathematical form all of reality. Well, here we had a brilliant test case. Einstein's theory clearly breaks down inside black holes. So what goes on? Is there some notion of physics? Is there some notion of science which we can think of, which we can conceive of, which really describes a kind of physical reality beyond where notions of space and time exist? That was the key question that Hawking set out to think about. And then he came up with that amazing thought experiment. You know what a thought experiment is? An experiment which you do in your head. It's cheap, it's quick, and when it comes to black holes, it's useful. So Stephen came up with a thought experiment. One of really, frankly, one of the best ones in 20th century science, I think. And his thought experiment was the following. All right, let's think about black holes, but let's do it sort of the opposite way around. Let's start first with an empty space. But let's think about that empty space in a fundamental way, in a microscopic way. Microscopically, we know that the world of particles is governed by what we call quantum theory. Quantum theory has a certain fuzziness. The microscopic world is fuzzy, is probabilistic. And if you were to look at the empty space in great detail, at small scales, you would see that it's not at all empty. That constantly, because of the fuzziness of the underlying quantum theory, virtual particle pairs, a particle and an antiparticle, are constantly being created and annihilated, created and destroyed. That's just how empty space is in a microscopic picture of our reality, studied, for instance, at CERN and at accelerators. Now Stephen thought, well, good, fine, let's take this as a given, but let me add a black hole to it. Look carefully. This is an illustrated talk. See what happened? Should I do it again? What Stephen thought, to his great surprise, near the surface of the black hole, these virtual particles can become real. Occasionally, you have these virtual particle pairs being created near the surface of the black hole, near the region where, if you were to go there, you're drawn into that deep valley of space. If you stay here, you can escape. If you have these virtual particle pairs near that region, well, occasionally, one of them is created inside the black hole, and it's bound to go inside, and it can exist there, and the other one is then free to escape. And the net effect of this is that there's a flux of radiation emanating from black holes. Black holes aren't as black as they are usually painted. They have a temperature, which Hawking calculated. This is the formula for the temperature of black holes. It's the only formula which I'm going to give, so enjoy it. So what's so special about this formula? It has all these letters in it. We're not going to talk about these, right? So what's this one? This is Planck's constant. It's the constant associated with quantum theory, which basically sets the measure for the fuzziness of the microscopic world. C is the speed of light, most of you will know. G, all of you will know, right? Secondary school, Newton's gravity constant. Pi, 3.14. K is Boltzmann's constant, which is a constant associated with statistical physics. M is the mass of the black hole. Now, what really makes this a truly special formula is that all these letters, all these different constants of nature are right there in one single formula. There is no other formula, even today, which combines all of these different branches of physics, the large, the macroscopic world, the microscopic world, relativity, into one single formula. It has never been tested, but everyone believes it because it's so beautiful. It's so beautiful that Hawking wanted that formula on his tombstone, and so happened. This is the stone of his grave in Westminster Abbey, and there is exactly the same formula. But it raises serious questions, serious questions. If black holes have a temperature, if they radiate, well, they're going to lose energy. Radiation takes energy away from the black holes. If they're going to lose energy, then they're going to shrink. If they're going to shrink, their mass is going to go down, so they're going to radiate faster, and in the end, the whole thing is going to disappear. So, wait a minute, that's a serious issue, because normally in physics, we try to describe the evolution of things, and we try to keep track of stuff. Otherwise, physics becomes random. So if we form a black hole by some collapsing star, if we apply Hawking and wait sufficiently long, it's going to disappear into some radiation, and that's going to be the end state. Now, the problem is the following. The radiation, as calculated by Hawking, contains no information whatsoever about what made up the black hole in the first place. So if you throw in Trump, or if you throw in Obama, you get the same thing out, and this is clearly impossible, right? Impossible. Okay? So something's wrong here. Something's wrong. Information is lost in this process. And so Hawking enjoyed writing papers at the end of physics, breakdown of predictability, guys, to challenge his colleagues, right? And so the question arises, where are the bits, the quantum bits? Where are the bits storing the information inside black holes? Hawking he even betted a few of his colleagues, challenging them from God not only plays dice as the quantum theory does, but he also sometimes throws the dice where they cannot be seen. But his formula gave a hint. It gives a truly amazing hint as to where these quantum bits might be. And that hint has serious implications. And that goes as follows. Any object with a temperature, which radiates, also has some kind of structure. It can't be just like empty nothingness doing something. So there must be some kind of internal structure to this black hole. The internal structure, the degrees of freedom, the information inside black holes, or inside any object, is captured by the entropy. The entropy is a sort of a measure of the number of ways you can make up a given object, like a black hole here. Normally, if you make an object bigger, the entropy goes up. The entropy is what we call is proportional to the volume of an object. If you have the temperature of an object, you can calculate its entropy. And to everyone's surprise, it turned out that for a black hole, in contrast to any other object we know in the universe, the entropy of a black hole is not proportional to its volume. In fact, the entropy of a black hole is proportional to the surface area of a black hole, to what's surrounding it. That gave rise to the idea that probably the bits storing the information associated with black holes are not inside. In fact, they're stored probably right on the surface of black holes. But if they're stored right on the surface, then I might as well forget about the inside. In fact, fundamentally, the inside doesn't even exist. Because if they're stored on the surface, I can formulate my entire theory of black holes in what we call a holographic way, in a mathematical form which makes only reference to the surface of the black hole. Black holes are basically holograms emanating from a lower two-dimensional, more fundamental theory. That is work that goes under the name of holography. Now you might say, well, okay, good. I don't like it. Huh? And maybe if you buy me enough cocktails, you might ask, well, if you go inside, what happens? If I can't resist, what happens? I'm telling you, there is no inside. And you give me another cocktail, and you say, well, go inside. What basically happens, I think, I am sort of getting a little shaky here. What happens is that the notion of space doesn't really make much sense in an Einsteinian way when you go inside a black hole. What can happen is that, like in quantum theory, that the quantum, the microscopic nature of the world, begins also to apply to space itself. And therefore, that the notion of space gets a little fuzzy, that the notion of time gets a little fuzzy because Einstein couples space and time, and therefore that the notion of evolution gets a little fuzzy, and therefore that you get some sort of multiverse inside these black holes, which push the information out to its surface in some delocalized, uncoded, hard to disentangle form. And that is indeed the kind of picture which emerges from, by now, several decades of work in string theory, which aims to bring together the gravity Einsteinian worldview with a quantum perspective on the world, and which more strongly and strongly suggests that fundamentally our reality is not made up of space and time, but some more delocalized version, a fuzzy version of reality, which goes under the name of holography or holograms or whatever you like. Now, the real game, right? Armed with this picture of black holes, let's now talk about the universe. Let's get serious. Now, I don't know about you guys, but we think in Belgium that the Big Bang, so the second subject of this book, we say in Belgium that the Big Bang was invented in Belgium. By Georges Lemaitre, who was a priest and an astronomer. At the time, you could sort of get inspiration. And he was working with Einstein's theory of relativity, and he noticed that Einstein's theory of relativity, when he was applying the whole thing to the cosmos, that it predicted that galaxies would move apart towards the future. So then he said, well, wait a minute, space expands towards the future. If I turn backwards towards the past, surely these galaxies are going to be closer to each other. And at some point in the past, there's bound to go something wrong. That's again because, as I mentioned, Einstein's theory connects mass to geometry. So if the mass gets packed, of the entire universe gets packed together, then the geometry is going to react. And if you exaggerate, the space fabric and space-time fabric is going to disintegrate. And that's what then Lemaitre referred to as the beginning. So here's a cool picture of the two gentlemen talking over the origin of the universe, in which Lemaitre says, well, if we go back in the course of time, the notions of space and time would altogether fail to have any meaning. And Einstein says, again, bad luck for him, right? Your calculations are correct, Dr. Lemaitre, but your physical insight is terrible. Again, he saw the problem, right? If Lemaitre was right, his theory was in deep trouble at the Big Bang. And so Einstein resisted for a while accepting those conclusions. In fact, Einstein is famous, basically, as you get the idea, right, for coming up with like a wonderful theory, beautiful theory, and then not at all accepting its implications. Anyway, it turned out Lemaitre was right, but he had to wait decades, right? There's a famous milestone in cosmology. In '65, two engineers of the Bell Labs near New York who were building radio antennas for intercontinental communication. Wherever they turned their huge disk, they measured some sort of noise, some sort of radiation, which really annoyed them. Well, they were engineers. They wanted the thing to work properly. It turns out that, in fact, what they were measuring was the afterglow of Lemaitre's Big Bang. If the universe was very hot in the beginning because all the matter was compressed, then surely it was radiating. And because the universe is everything there is, when it expands, the radiation can cool, but it can't disappear. And that's what we see today. We see today, wherever we look, even inside here, this room, there's a faint radiation, very, very cold, 3 Kelvin, 3 degrees above absolute zero, but it fills all of space, and you could map it. That's a sky map of that radiation. So you look out at the sky, and you don't look at the stars or the galaxies. You look behind all that, and you measure the radiation from the Big Bang. You can make a map, like you can map the Earth, and that pretty much gives you a snapshot of the universe, how it was a couple of 100,000 years after the Big Bang, when this radiation began to flow freely. And so given this, given the fact that the universe was hot, given this radiation exists, it is sufficient as observational input to conclude that if Einstein's theory of relativity is correct, then there must be a beginning of time. It's unavoidable. That's the thing. That's the real pain for Einstein, right? It was unavoidable. You could prove on the basis of his own theory that it predicted its downfall. And so now he really had a problem. Because in the case of black holes, you might say, well, fine, okay. I am just not interested in the inside of black holes. I'm not going to think about it. I'm outside. It's your problem. But in the case of cosmology, if there's this issue with the Big Bang, it's about you. This is our past. This is our identity. And without getting a grip on the Big Bang, fundamentally, we don't know where we come from. We are just the remnants of the physical conditions on how our universe came to be. And the real problem is that we appear to live in a fucking special universe. We appear to live in a universe which is mysteriously delicately fine-tuned in order to bring forth billions of years after the Big Bang something complex like Christiania, right? I mean, all these collectives here. So there must be something special about the Big Bang in order to get the universe going in just the right way that you end up with something which can harbor life, which is habitable. Gravity must be weak, because otherwise we would be crunched. 3 space dimensions is very handy. If you had 4 or 5, you wouldn't have stable planetary orbits. We have a bit of dark energy, but not much. If we had a lot, stars would never have formed, and so forth. The list is long of features of our universe which seem just right. And so the question about the completeness of the laws of science became much more important when the whole enterprise was applied to cosmology and to the Big Bang. And this is the core of Hawking's thinking. That's the real starting point for my conversation with him. It's what defined his thinking for decades, and in fact, it's nicely again, Hollywood. It's nicely pictured here in this movie. Huh?
And then, of course, we have chapter 4, this black hole at the beginning of time.
Space-time singularity.
Indeed. It's brilliant. Brilliant, Steve. Superb. Therefore, all there is to say is well done. Or perhaps I should say, to be more precise, well done, Doctor.
Bravo, Steve.
An extraordinary theory.
Thank you.
So what next?
Prove it. Prove with a single equation that time had a beginning. Wouldn't that be nice, Professor? So one simple, elegant equation to explain everything.
Yes, it would. It would indeed.
Thank you.
So that was basically his central goal for the rest of his career. We move backwards in time from the present day all the way back to a few 100,000 years before the Big Bang, where we had a hot universe radiating, which we see now. But then what? Ultimately, Einstein's theory breaks down. And in fact, when you do so, following the equations of Einstein and insisting on their validity, at some point you reach a phase in which the evolution becomes chaotic, and in which our evolution here gets mixed up with all sorts of different possible universes. Basically, if you insist on Einstein's theory backwards, you end up with a multiverse. An ensemble of possible worlds, like bubbles in boiling water, of different kinds, perhaps even with different local laws of physics. And again, basically, in essence, a breakdown of predictability. Because good, fine, and now what? Where are we? And what should we observe? And in what kind of world should we find ourselves? And so we did another thought experiment together now, in order to get a grip on this. And the thought experiment was, all right, let's go backwards, but let's not insist on the validity of Einstein's theory. Let's think about the whole universe from a quantum perspective. When the universe is large, this doesn't really matter. But it turned out when we went backwards in time, that quantum theory became important, and that the evolution further backwards is not governed by Einstein's theory, but just like black holes, that the notion of time evolution backwards was basically no longer happening. The whole evolution is turning into, again, a hologram. But in this case, it's not space which is disappearing, as we saw in the case of black holes. It's the further time evolution which is disappearing. And so we were led to a picture in which, instead of getting into a huge mess of a multiverse with infinitely many possible worlds, we are led to the picture of, wait a minute, we've pushed Einstein's theory too far. It's like trying to use it to go inside black holes. If you do, you end up with really a kind of bifurcation of reality in many realities. Similarly here, if you go too far, you're really pushing Einstein's theory where it doesn't apply. But rather thinking about it quantum mechanically, and you see that the world more and more becomes delocalized, fuzzy, holographically represented. And what is that hologram? It's a kind of ultimate horizon to our reality. It's a kind of boundary, a kind of very abstract state from which you gradually our universe in familiar notions of space and time emerges. The way Stephen described that holographic state is as follows. The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. Now the key question, this is all good and well, fine, okay, we get some different handle on the Big Bang. Time, we lose our notion of time basically on our way to the Big Bang, and therefore avoid that catastrophe that you get when you extrapolate Einstein's relativity. But the key question is, of course, well, now what? What kind of universe can emerge from such a holographic origin? And it turns out that that hologram as a model of the Big Bang predicts a very special universe. It can only get universes going which come into existence in time, so to speak, in a phase in which the initial expansion is very, very rapid, much more rapid than it is today. We call this cosmic inflation. So somehow from that holographic, delocalized, fuzzy quantum origin, say, time, or the dimension of time, can only crystallize in a way that gets the universe going in an extremely rapid, short burst of expansion, so to speak, inflation. But that has a very, very special effect. It has the same effect as what we discussed earlier for these black holes. If the universe expands very rapidly, these virtual particle pairs, now, because of the rapid expansion of the universe, they're going to be torn apart. They're going to be converted again into real particles. And look what happens. The radiation, the afterglow of the Big Bang, won't be completely the same anymore. These real particles, they manifest themselves as flickering. The radiation begins to flicker, begins to change from one place to another. These different colors here represent temperature difference, temperature fluctuations in the Big Bang afterglow, which is a very definite prediction of having an origin which comes together with inflation. So now what? Let's say, aha, good. So there's an experiment. Now we can look and measure the radiation. This was the picture I showed you in '65. But that picture was taken by engineers, right? Who, furthermore, they weren't looking for it. Since then, physicists have gotten their act together and have done their own measurements, more precise, and indeed, the afterglow of the Big Bang is not what people initially thought it is. It does flicker. It's not exact. It doesn't have exactly the same temperature everywhere on the sky. There's a pattern of fluctuations. And cosmologists continue to study that pattern of fluctuations in order to learn more precisely how that very early phase of inflation happened. Now, those fluctuations are important. Those fluctuations are crucial. They're basically you and me. Those fluctuations, which themselves arose from the amplification of these virtual particle pairs at the universe, at the Big Bang, at the origin of our time, those temperature fluctuations in the afterglow gradually evolve millions and millions and billions of years later in the stars and the galaxies we see today. If these fluctuations had not been there, if the Big Bang afterglow would have been the same everywhere, same temperature, then we wouldn't have been there either. This is an amazing synthesis. It's the beauty of cosmology, to connect our existence today, here on Earth, basically to the hologram at the origin of our world. It's a kind of evolutionary synthesis which brings Darwinian evolution on Earth and chemical evolution throughout generations of stars into one grand cosmic scheme. And furthermore, that evolution is not a pre-given. It's our observations today which really shape, which really decode the hologram at the origin of time. It's above all a human adventure. By studying the Big Bang, we learn a lot about ourselves. And indeed, Stephen was above all human too. Thank you.